Lecture 1.3 is going to review the stoichiometry 1 ditto in parts. Questions 1, 2, A, and B should be straightforward stoichiometry. I'm going to do number 1 for you, and then also I will flip it on its, I'll go on the back page and do, I believe, number 3. And in this way, we'll review all the basic concepts of stoichiometry and percent yield and percent deviation. Okay, so number 1, what we have here is we have a reaction between mercury oxide, so HgO goes to mercury and oxygen, and that should be mercury at H2. So Hg, okay, and then O2. Now, of course, elemental oxygen is always O2, and then we have to balance 2 here and 2 here. I'm not reviewing balancing. Obviously, what we're doing when we balance is making sure that both sides of a reaction have the same type and same number of atoms. Conservation of matter is what we talked about last year and still applies here. So you can't do any stoichiometry unless you have your reaction balanced. Stoichiometry in review is nothing more than the concept of using these ratio of moles in a balanced chemical reaction to solve problems where we start you with information about one compound and ask about another. Okay, for instance, in this case, we're heating mercury oxide. It decomposes as a decomposition reaction or a redox reaction into elemental mercury and molecular oxygen. So they're giving me information about the grams of mercury. Okay, and if I have 60 grams of mercury, is obtained from 80 grams of the oxide, what is the percent yield of the reaction? So what they're saying is, how much should I produce, okay, of my, okay, so if we have 60 grams of mercury and it's obtained from 80 grams of the oxide. Of course, the oxide is the mercury oxide, which we have here, so like the silver oxide we had in the lab. So we have 60 grams of it, 60.0 grams of it, and it's obtained, okay, I'm sorry, 60, I am all over the place here. I have 60 grams of mercury. Okay, I can do this. So I have 60 grams of mercury. Lecture AP 1.3 is on stoichiometry, percent yield, percent deviation, which last year we called percent error. And we're working with the stoichiometry 1 ditto. And I'm going to do number 1 and number 3 and model those problems for you. And I expect from those modelings that you should be able to handle the rest of this ditto. If you see that this is pretty simple, you certainly could move on, but just a review of stoichiometry in general. So in any case, what we have in this problem is we have mercury oxide, HgO, is being decomposed by heat, a lot like we did in lab with silver oxide, and we decompose it into mercury. Well, we didn't do this, but, and of course oxygen. Elemental oxygen is diatomic. And of course we're going to balance this. Okay, and that's our balanced reaction. Now, stoichiometry requires that a reaction be balanced because we're using the law of conservation of mass and these mole ratios to answer a question about one compound from another. So in review, what we have here is we have 60 grams of mercury has been produced from 80 grams of the oxide. So we produce 60 grams from the oxide, and we want to see what our percent yield is. So percent yield is equal to the actual yield, which is from experimental work. That's what this question is giving you, the experimental values, over the theoretical, okay, which is from pencil and paper, assuming absolute no error, okay, times 100, of course. What I mean by theoretical is, of course, assuming there's absolutely no error, how much mercury should we produce given 80 grams of mercury oxide with absolutely no error involved in the process. And we do that in pencil and paper type of stoichiometry. So we're going to do that now, and I'm going to change up the color because I can do that. And I'm going to start with my 80 grams of mercury oxide. And what I'm going to do is do a stoich problem. I'm going to take the information, which is the 80 grams of mercury oxide, and I'm going to figure out what my theoretical should be. Okay, assuming no error. This value here is what I got with error. Okay, so in any case, 80 grams, and it's good practice, and I'm going to start from scratch again, to write the grams with the compound exactly. What I mean by that is in stoichiometry, we're going from one compound to another. It's good practice to write that compound. So we have 80.0 grams of mercury oxide. We're going to use that as a unit. Okay. Now the biggest mistake here is that if I have grams, I can't multiply by a mole ratio. These numbers called coefficients. Okay, I have to be able to go to a how many number, and of course that's where mole comes in. So 1 mole is how many grams of mercury oxide? Well, I need the formula mass of mercury oxide, and HgO is very simple, is 1 mercury. Okay, so that is, I believe 108. Let me just look on my periodic table. No, wait, it's 200.59. Terrible. Okay, they're really heavy. And of course I have 1 oxygen. I think it was 10. And of course they round that to 16 in your reference table. I'm giving you the values in your reference tables. Okay, add them together and I get 216.59. And that's grams per mole. And that's just the formula mass you've been using. So 216.59. So my grams go. And now I have moles of mercury oxide. Okay, that's okay, but it's not exactly what we want though, is it? We want to answer about the mercury, so we want to get rid of mercury oxide, so we have to write that on the bottom. And we want a mercury using our units. Now what's the ratio? Well, it's 2 to 2 or 1 to 1. You may say, Mr. Krotsky, why do I have to even write the 1 to 1 if it's going to balance out? It's good practice to do that because it won't always be 1 to 1. Okay, so mercury oxide is canceled. Now we have moles of mercury. And last thing we want is grams. Get rid of my mole's above. We want grams. And how many moles equals 1 gram of mercury? As we just said, it's 200.59. Okay, and my moles go away, and I have grams of mercury. We put that through our calculator, and what we get is 74.09 grams of mercury. That is our theoretical value. That's the value that we would have gotten assuming there is absolutely no error. That's the maximum amount of mercury that we can expect to produce in this reaction. And that is going to be our theoretical. Okay? Our actual, of course, was 60. So when you plug that in, and I'll do that above here, 60 over 74.09 times 100, because we're getting a percentage. I put that in my calculator, and I get 80.98. So my theoretical, or my percent yield, I'll do over here. My percent yield is equal to 80.98%. Rounding with percentages, it's usually very, very nice to do 1 decimal place, but as you remember, a percentage has no units, therefore there's no significance in those digits. You can round any way you'd like to, and it should be correct. So if you said 81% or 80.98, give me more, doesn't matter. So 80.98 works for me, or 81%. Again, how you round it with percentage is up to you. So that's how they do that. If you were going to do a percent deviation or a percent error like we did last year, what we would have done is we would have done the subtraction part. We would have taken our known, if you remember percent deviation, our theoretical is 74.09, and and we would have taken our measured value or actual value of 60 minus 74.09. Now, they didn't ask for this in the problem. I'm just reviewing this as a percent error we called last year. Now we call percent deviation. How far away we from this standard or this theoretical. When you do this math, and I know they didn't ask for it, I'm just showing you if it does, and I think question 2B asks for it, so I'm just modeling it. Minus 74.09 divided by 74.09, and of course times that by 100. Notice I get a negative 19%. Around that to 19.01. I'm just going to round to 19%. Okay. Notice to negative 19% because our value is under, and it's good to use negatives in plus or minus error. How much are we under or over? Okay. Notice percent yield is always going to be positive, but percent deviation, it's a plus or minus error. How much you're above or you're below your number. Okay. So that's a review of number 1. You should go on to 2A and 2B. They're very similar. I have the answers on the key in the file cabinet for Unit 1, for Semester 1. And now I'm going to go on to number 3. Okay. Now the first thing I'm looking at when I see number 3 is that it is not balanced. Okay. So we need to start with a balanced chemical reaction. Now, if you think you need some practice balancing, I'm not really going to go over this in our course, something that it's a basic skill that we should already have, but in essence, in review, what I'm doing is I'm making sure that every single number and type of atom on both sides is the same. For instance, I have 1 carbon here, 1 carbon here. Okay, I have 4, I have 7, okay, I only have 3. Okay, so in essence, I'm going to throw a 2 here. Why did I do that? That gives me 8 hydrogens, and now I have, that gives me another terrible number. I'm going to throw number 2 here. That gives me 6. And then, of course, I have 8, 14, okay, and balances out this way. And you certainly can work that out on your own. I'm not going to walk yourself through that, but those are the coefficients I get when I balance. Okay, there's not one way to teach this. You go ahead and figure out those values, left to right, right to left, however you need to do that. But you should come up with that balanced reaction. Okay, so getting back to, and of course, these are the mole ratios we would use, okay, in our stoichiometry problem. Okay. So this problem is a little different from one and 2 in the front page, in that we're going a little backwards. And let's talk about this for a second through the question. If the yield is this, so you notice I'm giving you the yield already. So this is the percent yield. So giving you that the yield in this process, this industrial process, is 97.5. How many kilograms of methane and ammonia should be used to produce that many kilograms? So I'll say this again. I'm giving you the yield. I'm not producing the yield. They want to know how many kilograms of methane and ammonia is needed to produce a certain amount. And this is more of a realistic problem than 1 and 2. We usually have the percent yield given the process in an industrial plant or a chemical plant already. We already have this number down. So given our efficiency, okay, of 97.5, and taking into consideration there's going to be some error, how much should we produce? So we're going backwards a little bit. So if you think with me, the 97.5 is considering the error. So we're thinking about, well, how much methane? Now, what some people might do is take this 1.50 times 10 to the 5 kilograms of hydrogen of this HCN here. Okay, and they say, okay, I've given this many grams, I'll just take it to a stoich problem and figure out these values. Now, if you were to do that, take this value and do a stoich problem backwards, okay, think with me, would you be overestimating or underestimating? Well, you would be underestimating. Remember, this value, 1.50 times 10 to the 5, is what was made okay, from these two reactants with error, meaning some of this probably did not react. Remember, 97.5 efficiency means that, well, we lost 2.5% didn't get produced. So that means some of the methane and nitrogen or ammonia was lost in the process, or didn't completely react, or there was side reactions. So if we were just to go backwards, okay, and from the 1.50 times 10 to the 5 kilograms of this, and not consider what was lost, then we would, if you think about that, you'd be overestimating. I'm sorry, I misspoke. Okay, you would be underestimating. Okay, and let's just think about this for a second. Okay, if we have 1.50 times 10 to the 5 kilograms being produced, if we were to go directly back in stoichiometry and find out these values that were needed to make, we would be assuming that 100% efficiency going backwards. Now remember, if there's some error, some of this would escape or wouldn't react a little bit. We have to account for that. We need all of that. So you would actually get numbers, okay, that are smaller than necessary if you go back without error. We need to account for the stuff that's lost. So when we use the efficiency, we're going to need that extra, okay, amount that's going to be lost to get that, okay, if that makes any sense at all. So the idea here is that we cannot go directly backwards because we would get values that would be under what was needed. But we're going to have some error, which means we're going to need to consider the extra that didn't react. We're taking into consideration the error in the process. If this was 100% efficiency, we could do that. So to consider the error, these values have to be larger than necessary because we have to consider what was lost in the reaction vessel or due to the error in the process. Okay, so what we're going to do is we're going to start with a formula, and you may not need it, I'm just laying it out for you. Percent yield. Okay, again, over the actual, over the theoretical yield, times 100. Okay, well, rearranging this, you should get theoretical yield equals actual over the percent, of course, times 100. Okay, so my theoretical yield is what I'm trying to solve for. I have the actual, which is 1.5 times 10 to the 5 kilograms. I have the percent yield, which is 97.5%. We'll just make it 0.975 to get rid of the 100. Okay, and from this, I get and solve for my theoretical yield, which is 1.538 times 10 to the 5. Now look at that for a second. As I change inks, look at this. This is the theoretical yield. All I did was manipulate our simple percent yield equation, solve for theoretical, and look at this value. This value is larger. Okay, this is the theoretical yield that we would have gotten if the amount I'm starting with would have gotten me that to the promised land. Meaning, you can see that the 0.038 difference between these two numbers, that's the difference in the percentage. Meaning, that is how much extra we're going to need to make this number. So we're going to go backwards from this value of hydrogen cyanide. And now we're going to find, okay, ammonia and methane that was needed to make that amount. Starting with that theoretical. Now, why? can't start with this. If I start with this number, which is the actual, and go backwards, these values, okay, would be smaller. As I just pointed out and made that mistake, they'd be underestimated. We need more of them to make that extra 0.038 theoretically. Now, that's theoretically. This is what actual happened. How come there's extra? Well, because we have some error. We lost some. So we need to have more of the CH3, or I'm sorry, CH4 and the NH3, okay, than it's required to make the actual because some is lost. Hope you understand that process. So in any case, I'm going to get rid of some stuff in my way here. Now we're going to do some straight stoic problems. I've now come up with my theoretical, which assumes that's how much I would have made if there was no error. And now I can go back. So given that value, okay, now it's just a straight stoic problem. 1.58, okay, 1.538, classic, I didn't make a okay, and 1.38 times 10 to the 5 kilograms. And I'm going to convert to grams. Certainly you could have skipped this step and done that. I just have to lay everything out in front of me, organize my thoughts. 1 kilogram. Now I'm into grams. And now, of course, I'm going to go to moles, into a how many. So I need a formula mass. And this is, we're going to say this is for hydrogen cyanide first. Okay, you do the formula mass of hydrogen cyanide. You get 27.025.02 0.0257. Okay, this is 1 mole. Okay, notice grams cancel. And then, of course, I'm going to use the ratio. I'm going to get rid of hydrogen cyanide to get what I want. In this case, we're going to go to, let's go to methane first. It's one of the reactants we need, CH4. And it just so happens to 2 to 2. So you could obviously skip this mathematically, but I like to write it out just to keep myself organized. Now I have moles of methane. Let's get some of this other stuff out of the way. Okay. And the last thing we want is grams. So we put 1 mole on the bottom. And the formula mass of methane is 16 point, what do I have here? 0.428 grams, and the moles cancel. Put that through my calculator. Notice I have it all set up. I have grams of methane. I've got 9.13 times 10 to the 7 grams, and of course that is methane. And I'm going to do this one more time. This time I'm going to do it for, again, we're both starting it with hydrogen cyanide, and now we're going to do it for ammonia. So a lot of this looks similar. 1538 times 10 to the 5 kilograms. Okay, I'm just converting to grams using my units. And same idea, 1 mole is equal to 27.0257 grams. Grams go away. And now we're going to get rid of hydrogen cyanide, just 2 moles of them in the balanced reaction. And now we want ammonia. It's also a 2 to 2. I keep showing you examples that are just 1 to 1, sorry, but there are always going to be many more examples of that non-1 to 1. Okay, so I've got moles of ammonia, and what I want, 1 mole ammonia is about 17.03 grams. That's the formula mass, 1 N, 3 H's, adding them up. And of course, times them together, I get 9.69 times 10 to the 7 grams of ammonia. Okay, so this is the 2 answers, and again, these values, okay, are larger than what we would have gotten if we started with this value. Okay, so the reason why these are larger, well, than what we have gotten, because we had to consider the error in the process. And this is what we actually do in chemical industry. We know the efficiency of the process, given that, taking into consideration the error, exactly how much of our reactants do we need to make a certain amount given the error. Okay, so that's number two. Try number four. Nothing earth-shattering, just a little difference in understanding going backwards in the problem. We're done.